Hello and welcome to our today's training, RFM 6 for Students, Introduction to Timber Design. My name is Jürgen Thalmann and I work for Dluboy Software in the customer support. This is where I answer your questions about the program. And today I will be the host of the training and I will guide you through the models we're gonna analyze today. By my side is Rebecca. And Rebecca, you can introduce yourself.
Yeah. Hello, my name is Rebecca Göbel and I work at Dluboy in customer support and also in the development for web service and API. And today I will answer your questions during the training.
Yes, thank you, Rebecca, for your introduction. We're gonna switch off our cameras so you can experience the whole presentation in full screen mode. And we'll jump into the PowerPoint. And first of all, Rebecca mentioned that you can ask questions. There's a small rectangular question mark at the top right of your screen right now in the Go to Training panel. And if you click on that question mark, you have the possibility to submit your questions here. And also, if you have problems listening to me, you can adjust your audio settings on the right top of your GoToWebinar control panel. So to the whole training series, this is now the one part of our training series, RFM 6 for Students. We are now in Timber Design. And in this session today, we're gonna tackle 4 different models in which we're gonna start with a very introductory example, a timber column, where we only perform one design check, the stability design check for this column. And in the second example, I'm going to tell you something about design support and notches in timber members. And finally, in our examples 3 and 4, we're going to model some simple examples for timber design where we can see some features in the add-on and in RFM itself. Okay, before I'm going to jump into RFM 6, I'm going to have a question for you. So I will start with the first poll, which is the question, have you already carried out timber design using structural analysis software? I'm going to launch the poll now, and you have the possibility to vote now. Okay, I'm gonna close the poll in 3, 2, 1, and I will share the results. So the majority of yours have not yet performed timber design in a structural analysis software. That's very good because we're gonna show the very basics today. So I will close the poll and jump into RFM. And I will start with, like I said, with a single column. So I will open a new file, create a new model, call this number 1. Timber column. It will be a 3D model. And I will save this under my existing projects. I go to the trainings, introduction to timber design. Okay, because we're going to perform timber design, I will need the add-on for this. This is here. And also I will choose the standards I'm going to design by. So this is now the load classification, Eurocode 0 or EN 1990. But there's one special thing in timber design. We have an extension for that for that standard. I'm going to show you later what this means, but every time you want to perform the timber design, you'll either have to use EN 9090 Basin timber or EN 9090 timber. Okay, the design checks themselves will be performed according to EN 9095. That is correct. And I will say OK to create the model. So we now have some basic materials, basic objects from the last model I had open. So I will just clean up this model. So we can start with a blank page like every time you will start a new model. Okay, and now just to make this quick and easy, I will create one member perpendicular to our working plane. So this is under the section New Member. You can fold out this subpanel and you can say single member perpendicular to the working plane. Now I will define my member. This will be a beam. We of course need a section for this. So we need a new cross section. Let's make this one a parametric massive, a rectangular cross section. We need also a material for this. So I will choose the library for our materials. This is already set to EU and timber. Usually you start without any filter, but you can set them as well. This was the softwood. Where is it? Solid timber. Yes, the softwood C, and we'll make it a C24. Okay, now we have the typical color assigned to the timber materials, and we of course need dimensions for this rectangular cross section. So I go to the second tab and I give this one a width of 160 millimeters and a height of 200 millimeters. Okay, that's all we need right now. The design types and so on we're gonna tackle later. So we just start by setting this column. This should have a length of 4 meters. You can see this is now set to millimeters. So this is now 4,000 millimeters. And when I hover my mouse over the working plane, you can see that the member will be facing downwards in the positive Z direction. So I want to reverse that. There's also a button right next to the window where I entered the length. There's a button for reversing the orientation of the member. So this is now facing upright. And I place it right at the origin point of our global coordinate system. Okay, so I now go to options, units, and decimal places because this was set to millimeters before. So we can set this to meters to have our standard settings again. Okay, now we have the column and we also need our nodal supports for this. So I will set a nodal support, which is next to the modeling options. There's the boundary condition option. So I set a nodal support. This shall be hinged, but not the typical hinged one. I will also add a restraint rotational around the global x-axis. So I will edit this one, set the additional rotation fixed, and assign this to the bottom node of our column. I hit apply just to stay in the dialog because I want to assign another nodal support on top of this beam. So I create a new nodal support, which will only give support in the global X direction and rotational restraint around the global X direction. So you have the picture on the right, which symbolizes the actual nodal support. I say that's okay, that's the one I want, and assign it to the top node. Click OK twice, and there we have our supports. Good. Next thing is we will need a load case. So we already have a load case self-weight. I will edit this one because this is not going to be a self-weight. This is going to be a design load. So I will change the name and deactivate the self-weight for this. And now you can also see the reason on why we needed to change the standard for our load combination and classification system. Because when we don't use the extension timber, you don't have an option for the load duration. So I will just demonstrate this. When I go to the typical EN 9090, yes, and go back to the load case, you can see that the option for the load duration is gone now. And this is needed, especially in timber design. So I go back to base, set this one back to EN 9090 timber. That is very important. Okay, while I'm in this tab, I will deactivate the combination wizard because I want to use manually defined load combinations. So I have my load case. This will have a load duration of the type medium. And I will jump to the design situations. We will have one design situation for the stability design check. So I delete both design situations for the serviceability state. Now I skip to the load combinations. I want to create that manually, as I said. So I create a new one and assign load case number 1 to this just by double clicking on it. We have a load factor of 1.0. That's okay because we're going to enter the design loads directly into the load case. Okay, so now that is for the combination and the load cases. And now we will need to create a load in the load case 1. So from the boundary conditions, I skip the surfaces, and there I have my section of the loads. Make this one a nodal load in load case number 1. Say OK. And assign this to the top node, which is node number 2. And can now enter the parameters of my column. So this is going to be a force according to the global coordinate system in global Z direction. And it's going to be in another unit. So I will change the units for this. Need this to be kilonewtons. I would say I would just set my whole units and decimal places to the default settings. So we can now enter the load in kilonewtons. So this is 115 kilonewtons in the global Z direction. Okay, good. So when we now want to perform the design checks, we need some more information about that member. So I will double click on it. You can see that the design properties are activated, and therefore now I can switch to the additional tabs where I have my design types, where I'm going to start with the effective length, because in timber design, we usually work with a equivalent member method. So I just drop out the list and go to new effective lengths. Then I can select the determination type, and I will neglect the lateral torsional buckling for this simple rectangular cross-section. We're going to use the lateral torsional buckling later on, but this is now just flexural buckling about the major and minor axis of this very simple cross-section. So in the next step of our effective lengths, we need to define our nodal supports to segment our member. And like in any other dialog in RFIM, you can of course switch from this typical helping bitmap to the actual dynamic rendering of your model. Now you can also see that orange representations of those nodal loads we have. So at the bottom, this is okay with the standardized fixation in both local axes Z and Y. But on top, you know that this global nodal support is just in X direction and not in Y direction. So we need to release that nodal support in the Y direction as well. I check the global coordinate system with the local coordinate system of our member, because the local coordinate system gives us the directions for our supports for these effective lengths. So the local Y direction is by coincidence the same as the global Y direction now. So I open this up, and this is now according to the global nodal support. Okay, so this is now with effective length vectors of 1 in both directions. I'm gonna leave this with the default values, say OK. Skip to the next part of the design types, which is the service class. So we have 3 different service classes. We can edit them so you can see the effect of it and when you need to consider which service class. Also have a bitmap on the right, which helps you to determine the correct service class. Okay, I'm going to stick with dry in this case. Say OK, so we have service class number 1. And we can set local section reductions, which we're going to use in our second model. And we say OK. I switch to the design situation where I can click on this abacus symbol, or in particular open the subpanel and click on the timber design. So we run the calculation. And in the table, you can see the governing design checks for this timber column. So I will double click on the stability check, because like you have heard before, in every of these design checks, you can see and check the details for these results. So I double click on the stability check, and another window will open which shows us the exact calculations performed by the program to perform this design check. So I take a look at a few details. Let's go to the lambda values for the slenderness, and let's go to the equivalent member length. And I see there's something that bugs me a bit. So I go back to the column itself, double click on the member, go back to the effective lengths, and that's the one maybe you have stumbled over when I talked to you about this. When you have that bitmap about the effective lengths, you can also switch to the standard Euler cases. And there you can see when you compare it with our nodal support at the top that this column is not a typical Euler case number 2. It's a cantilever column around the z-axis. So when this has a load in or a buckling, an imperfection in the local y direction, this will have properties of a cantilever column. So we need to set the effective length factor for the bending around the minor axis to 2 instead of 1. So this is now correct. Say OK. Start the calculation once more, and you will see that the design check is now no longer fulfilled. So this is also giving you an example on why you always need to consider your input data and give it a second thought if you have really input your effective lengths in the correct way. Okay, good. Now there's another thing I want to show you in this. When I go to the input data, usually I prefer to use the table for doing the settings for the design add-ons. Of course, you can use the navigator data as well. But like I said, I prefer the tables. So I go to the ultimate configurations, double click on them. When I go to member stability, you can consider such creeping effects. When I activate it, you have a small explanations. This is a creeping effect or via reduction of the stiffness with a coefficient. However, this is only valid if you calculate and design by the German National Annex. So if you're not using the German National Annex, you don't have to consider this at all. Okay, I say yes and save the model. And after saving is done, I will jump directly into our second model for today, which is about design supports and also notches. So we have a small monopitch roof, which is wall mounted. So we have, turn around this thing, we have several nodal supports which represent our wall mounting, and we have a girder which goes across the whole roof to support all those rafters here. Okay, and we have already predefined, I just hide the load which is defined in this model. And we also have these pink thingies here. And these are the so-called design supports. And they have two main functions in timber design. The one thing is you always need those design supports if you want to determine the compression perpendicular to your grain direction, which is important. And the second thing, like in any other add-on where you have an serviceability state design check and design situation, that you need to segment your members and member sets for the deflection. So when you look at this rafter, you have a member set which goes from the wall mounting to that free end. But it's still supported at the place where it touches this girder. So this is now the exact length you need to consider for your deflection design. Yeah, okay, so I jump into the member of the girder, hitting a double click, go onto the design supports and deflection, and you can see that at the beginning and at the end there are the design supports number 1, and in those intermediate nodes you can also see the representation in this graphic down here, where you have the design supports for the rafters lying on top of this girder. And I will show you the details for the lower ones, the lower design supports, where I go to edit the first one. So you can imagine this as a column where the girder lies on. So this is another timber column, maybe the one from our first example. And this gives us an area where the girder lies on. So this thing is active in the Z direction. It's a direct support, and it has a length of 60 millimeters and a width of exactly the width of our girder. So we could also switch this off and say this is a bit narrower than our girder, so we can edit any value we want, or we stay by my first statement where this is exactly of the same width as the girder. Okay, we also need a factor for the compression perpendicular to the grain, which I will leave at 1.5. You can also use this drop down for some other predefined values with an explanation for which you need them, or you can also edit any value you need for your calculation. Okay, and I just saw there's one thing I'm gonna switch off first. This is for later. Okay, and now we will start the calculation once more. And now we can see that the design check compression perpendicular to grain is not fulfilled. And you can see the orange pointer at this very end of our girder. I can again check the details for my design check, and you can see that the effective area is really small. So if we can make this bigger to have a bigger load spread on the column, this would be better for this design check. So I will talk to our designers and say, let's change the dimensions of that column so we have a larger area. So let's make that supported length 80 millimeters, just a little bit bigger. And when I calculate now, you will see that the design check is fulfilled and also the governing one for our girder. So this is now with a design ratio of 90%, we have that compression perpendicular to grain at that end of the girder. Good, so another thing I want to show you in this model are the notches, or as we call them, the section reductions. So I had this one here already. I deleted it out, so I want to show you what this was or is. So I make a double click on that member, and I can see that the design properties are set for the parent member set. So I switch directly to that member set because I want to edit the design properties. So I go to the design types where I already have explained effective lengths and the service class, and now we go to local section reductions. So I create a new one for this. There are several types for our section reductions. Basically, we have 3 types of notches: at the start of the member, and at some inner point, or at the end of the member. So this will be a start notch. It will have a length of 40 millimeters. So this is now 0.04 meters. It will be oriented by the depth of this beam. So we need to edit the or enter a reduction value for the height of this cross section. This will be 100 millimeters. And it will be on the plus Z side. So you can either have this on the top or on the bottom side of this. And since we have our local Z axis facing downwards, the bottom side will be the plus Z axis. Okay, also this notch is at a nodal support, so I set this check active. I hit OK twice, 3 times. Okay, and now you can see this notch is now also in the rendering. Okay, we can calculate this once more. And you can see that we still have our compression perpendicular to the grain, and we also have our section proof with a notch at a support. So there's also a non-designable situation because we have the situation with a notch at a nodal support, but you can neglect that message because you have the section proof at this notch and you still have the compression perpendicular to grain. Okay, good. So this is for this model. Before we go to the third one, I will have another question for you. So I go back to my polls and I will give you a statement. And the statement I'm going to tell you is: for the verification pressure perpendicular to the grain direction, design supports must be defined. You can now tell me if the statement is true or false. Okay, I will give you another 3 seconds before I close the vote. 3, 2, 1. Okay, thank you. And I will share the results, and we have 100% true answers. That is great. Wow, I'm impressed. Good. Let's jump to our next model, which is going to be a dual pitch roof. So you may wonder, this is an empty model because we're going to set this model up now. This is just some prepared file with a material with some cross sections and some predefined load cases. So we don't have to bother with these details. So I will show you now a tapered beam or a dual pitch roof beam. So I will create a new member. This is again going to be a member of the type beam, and in the cross sections we can choose between different tapered and non-tapered distribution types. So this may be a typical tapered beam and tapered at the start of the member like you have in steel constructions. And I will show you the distribution type saddle. So this could be either a fish belly like this one, or you can switch the alignment. You can have this on the left, either centric or at the bottom. So this is the one we want to use now. And that inner point can also switch from various locations on the resulting beam. So I want to have this inner point K right at the middle. So I set it to 50%. Okay, and now I want to assign some cross sections. So I start at my point I, at the beginning of the member, just going to have cross section number 1 of my predefined cross sections. At the end, this is going to be the same again. So I leave this as it is, as member start. And the internal point K will have another cross section, the bigger one. So I choose from the list my predefined cross section number 2. Okay, material is also predefined, so nothing more to do. I hit OK and start from the origin point of our global coordinate system. Make this one really big, 24 meters. And there you have our dual pitch roof beam. Okay, now for assigning some supports, especially for our stability design, I will need some inner nodes on this member. So I will divide the member with a right click, go to member and say divide with n intermediate nodes. So I want to divide this by 5 nodes, and I don't want a real member division. I only want to create nodes of the type on member, so I still have one member in my system. So I say OK in this dialog, and you can see 1, 2, 3, 4, 5 of these blue nodes are created. Also, you can see the names of this members used cross sections. You can change that or hide this in the navigator display. When you go on members and you have the section name, you can hide this or show the name of this material. This is just additional information you might or might not need. Good, so we have these internal nodes. And now I will jump into the design properties of this beam. I have the design properties activated. I go to my design types and create effective lengths for this. So now with this glue laminated timber, we need to consider the lateral torsional buckling. In timber design, usually we go for the analytical method. You can also use an eigenvalue method, or if you have maybe your professor gives you a task where you need to use a user-defined critical moment, you can set this one to user-defined, but don't forget to edit the one in the next dialog for the effective length factors, where you have a possibility to edit that user-defined critical moment. But as I said, usually we use the analytical method. So I go to analytical and jump back to our nodal supports for this member. We still have our fork supports at the beginning and the end. Again, like I always do, switch to the dynamic rendering of the model. So we have these fork supports at the beginning and the end, but we in addition want to define some lateral supports on these intermediate nodes. So I hit the check intermediate nodes, and I can automatically take those intermediate nodes from the member by this picking function. So I pick the member and I have my inner nodes. So when I click on them, we have node number 4, 2, 3, 7, and so on. And we can simply click on these checks to add the lateral supports, either one by one, or you click the first and the last of those for a multiple selection, then hit on and off as you prefer. And you can see now we have our lateral supports. This directly affects our effective length factor for this. So we have a critical length that spans from one side to another of the beam for buckling around the major axis, and just for these small segments between the lateral supports around the minor axis. You can also add some eccentricity to those supports if you need to, but we don't need this here in this example. So I hit OK. This is going to be service class number 2, which is fine. I go OK. And now we can calculate the timber design. So I'm expecting an error now because I know this example. And this is another error I've made. I need to define my nodal supports. The ones I have edited are merely for the design checks, but not for the statical analysis. Now for the statical analysis, we need the green nodal supports. We define by, you know the drill, this button. Then we have the fixed support, which I'm going to assign to the left. Hit apply, and now you can see our familiar green nodal supports. And I go to my roller in X direction and assign this to the end of this member. So now we can start the calculation. There will be another problem because I have doubled nodes. And this is something that can happen very easily. I go to the table of my structure, and in the basic objects I find the nodes. This is where this arrow is pointing to. The problem is that with my section distribution I have created an internal node on the member right in the middle at 50%. This one is fixed and cannot be edited. It's a generated node. You can see that also by the purple color in the table. And this is locked and cannot be edited. And in the second step, when I created my intermediate nodes, I created 5 intermediate nodes, and this node number 6 is now identical to this generated node. And there's the conflict. So you can pretty easily get rid of this doubled node either by deleting it, or you go to your tools, the model check, go to identical nodes, where you can say you unite them and delete the unused node. So now node number 6 is deleted, and that internal node number 3 has the lateral support assigned to it. I go back to my timber design, and now we can perform our design check. Oh, where's my head today? I will I will need to go back one step because we don't have any loads right now. I totally forgot to do this, so let's go one step back. I will need member loads. I will assign them to our member number 1. And in load case number 1, we need some additional load. This will be 1.02 kilonewtons per meter in the global Z direction. I hit apply and next. You can see the load is applied, but we can directly switch to the next load case. Member number 1 have now 2.7 kilonewtons per meter in the global Z direction. Apply and next, then we have the snow load. Again on member number 1, 3.15 kilonewtons per meter, but now important for the snow load that we have the load in global Z direction, but not on the true length of the member, but on the projected length. Hit OK and have our loads, and now we can finally calculate. So we can now see our results for this. When I go to the graphics of the results, I don't use the envelope. I want to have the section proof. Let's say we only watch the bending about the major axis. You can have this cross-section check. And when I go to the stability check, you can also see the formulas used for this check. And also in the section proof, let's go to the bending around the major axis. And like in any other section proof, you can also see the cut to grain angle of 5 degrees because we have an angle right on top where the timber is cut through the grain. Yeah, okay. And also there for this type of sections where you have a linear cross-section distribution but a non-linear stress distribution, it's not always easy to find the place with the highest bending moment. So we have it about here with the 0.8 design ratio. You can see that it's certainly not in the middle. It's also not at the end of the member. It's somewhere in between. And I will show you something that might be a bit of a trap when you use these programs for the first time. Now go to calculate and go to my mesh settings. You might know by now that each element in RFEM will get an FE mesh. So also the members, these are meshed by the member divisions. So we can set these member divisions to a very little number of 2. Let's say go and apply. This will be meshed and I will calculate once more. You will have a design check like this, and this is a rather zigzag diagram, not the one we would expect. And also it's not possible anymore to see the place with the location with the highest bending moment. So I go back to calculate, mesh settings. Let's put this to the default settings. Now 10 is a bit coarse. Let's make this a bit finer, but 24 is too too fine. Let's make this 12 or something like that. Say OK, calculate once more. So we now see 12 is still a bit too coarse. So 24 was the way to go. Yeah, and this is basically the same idea you also got from the training introduction to FE analysis, where you basically always say that you need to keep the mesh as coarse as possible, but at the same time as fine as necessary. Otherwise, you would have a maximum of the bending stress at this intermediate node, when in reality it's a bit more to the inside of the member. Okay, and if I just jump to, let's say, load combination number 2 without loads, and we go to the static analysis and the internal forces of that member, you can see that we have a normal force in this member. We have a compression. This is resulting from the fact that the static line of our member is not at the same place as the geometric line of the member. So there's an eccentricity, and this gives us a normal force through the bending of this member. This is something neglected by the hand calculation, but in reality this normal force appears and of course has to be considered whenever you do a static analysis for such systems. Good. Now coming to our third question, I will start and launch the poll right now, which is another statement I will give you. I will read it and then give you the question. To determine the location of the maximum bending stress, a not too coarse member subdivision should be chosen. Is this true or false? Again, read it carefully. There's 2 no's in this, so yeah. Okay, I will close the poll in 3, 2, 1. Okay, so this is the majority is right. So to just get of this complex statement and get a right answer out of this, when I go to calculate in the mesh settings, I close the poll so you can see my screen. When I go to calculate in the mesh settings, when I set this to a number of 2, so this is a 2-coarse subdivision. So the member division is a member subdivision, and now we have a 2-coarse member subdivision, and by this we get a terrible result diagram. So the true answer should be a not too coarse should be chosen. So we go for the final one here because the results are rubbish at this point. Okay, so we will go to the fourth model. This is now a lattice truss. This is also prepared. We have again some load cases predefined. We have materials predefined and cross sections. And we start right away with a first member, which will be our upper girder of the lattice truss. So we have a beam. Go with the section number 1. It's okay. We start at the origin point and go some 14 meters in the X direction. And also what I want to show you in this example are the so-called member representatives. So I go to the model base data just to show you in the settings and options that we have an option of member representatives and member set representatives. So when I have these active, I get a wizard for those, and you can see now that this is now a consideration of member properties. So a representative is kind of a template for similar beams, for similar members, which can be grouped for the purpose of multi-editing and being quicker in modeling. Okay, so now we have one member, and in the middle there's this small red rectangle right where my mouse is now. So now I want to divide this member, and this time make it a real member division. So now I have two members, and you can see on both of these we have this red square. And when I click on this red square on the representative, both of these members are selected. And this can come in quite handy when we want to model larger structures. Okay, so I will move the middle node up a bit because this is now the upper girder. And this will just be minus 1.8 meters up. So we have something like this. Now I want to create the lower girder, make a new member, also type beam, cross section number 2 this time. Also pretty quick from the first and last node of the upper girder. So now when I dismiss this dialog with a right click, you can see this is now a different representative because it has a different cross section and a different length as to the two top members. So this is now another representative and gets another color for this small square. Okay, since I want to have some kind of a 3-hinge train for the upper girder, I will need to assign a member hinge. So I double click on the first one, the left, and in the options for this member, we can activate the hinges. We get another tab for the hinges and then activate or create a new member hinge. This was also predefined. We can also use the first one. This is the typical moment hinge, which I want to use. And don't worry because they are grayed out. This is just because this is now a 2D model, not a 3D model. Okay, at the end we have our newly created member hinge. I say okay, and I do this only on the left part of our upper girder because if I do the same on the right, we would create a hinge chain which would be an instant instability for all load cases, which we don't want and in reality don't have. Okay, this is now the hinge, and now we will need some intermediate points because I want to build the truss members in between those two girders. So now I select all of my members, make another member division. So we have 3 members selected. I divide those members with n intermediate nodes, make 2 of them, and again, like in the other example, make them nodes of the type on member. Okay, we again have our blue nodes at the intermediate points, and we will use them now for our internal members. Create new ones, make this a member type truss, and also assign another cross-section. This is now cross-section number 3, a squared rectangular cross-section of material softwood C24. Okay, and now I just create these crosses from node to node. So, and that's it for the modeling. Good, now we need the supports, so that I don't forget them again. We have a hinged one on the left. I apply and go to the roller in X direction. Set this one to the right. So this is the same drill as in the same model. And now we need our loads. Again, we have our 3 load cases, which is self-weight, imposed loads, and snow. And again, I will use member loads for this. Okay, I assign the loads to the upper girder. Then I will have 3 kilonewtons per meter. But in the load case imposed loads, the self-weight will be considered by the self-weight of the structure, so there's nothing to add here. This is a force uniform global in Z direction on the true length. I hit apply and next, go to the snow loads, choose the upper girder once more. This is now 3.5 kilonewtons per meter, and like before, the snow load will be global in Z direction on the projected length. Okay, so now we have this set up and we can calculate this once more. You can now see on my sheet of paper that I have forgotten something. We haven't assigned effective lengths right now. So I'm using the representatives now to define the effective lengths on the upper girder. So I click on that red square. I have both of them selected. Make a double click on them, go to the design types, and this is where I need my effective lengths. So these have also been predefined. So for the first effective length, I go to edit so you can see what I have done here. We have analytical method like before, and we have the effective lengths for those now set, which I have predetermined. And you can also set those as absolute values. So if you have the critical length, yes, as absolute value, you can edit this in meters, or you deactivate the check down here and you have the effective length as a factor, which is now automatically calculated to the length of these members. Okay, no section reduction, service class 1, that's okay. Now I go to the lower girder, which has only one representative. Also have an effective length for this, pretty much the same as for the upper girder. And for the trusses, they contain of 3 different representatives, but I can select more of them at the same time, pressing the control button on my keyboard. Now I have all of them selected. Go to the design types and assign my effective length number 3 for those. Say OK, and now we can do the calculation. Okay, so now we have our design checks. They are all fulfilled. That's good. Again, you can go to the details wherever you want to. And now we have our lattice truss calculated. Okay, so that's all for today. The basic introduction to the timber design is done. And I have one final question for you. Start this now. What are member representatives? Okay, I will stop in 3, 2, 1 and share the results. Yes, 2/3 of you have the right answer. The other answer, members grouped together like one single member, I will show you in this model. This would be when I go to one representative. So I select all members which are the same. So it's basically a template for members to group them. The other thing would be if I select the upper girder, make a right click on those two members and say create a member set. This is now a set of continuous members and they can be treated like a single beam in the design. So this is the second answer would be the member sets, and member representatives is the one. It's a template for similar beams with identical properties. Okay, that's all for today. Thank you very much for your attention. Have fun. Have with using RFIM and other products from the Dluwal software family. And also, I wish you the most of success with your upcoming studies and your projects lying ahead of you. I say thank you and hope we will see you again in a further training or webinar. Have a nice day and goodbye.